previous talk, a bit different. Like any story, there should be some friends, there should be some enemies. I hope there's going to be some character development, otherwise it's a rather boring story. And also, of course, there should be a moral at the end, and hopefully some questions to follow on from it. Of course, I'll be talking about Wiener-Hopf, and the first thing I'll be talking about is the differences between the pole removal method. So the pole removal method is the most frequently applied method in applied Wiener-Hopf community. And the differences to the kind of the classical Wiener-Hopf factorization. That would be the starting point. And then I'm going to go, well, maybe all we need to do is to do some rational approximations, maybe some mappings, and we can just solve everything. And of course, the answer is no. And the reason, somehow the reason the answer is no dates back to the original paper of Wiener-Hopf, and the mistake that they have in that paper is very much related to the answer why rational approximations are not the answer to everything. And then going on forward from that, I will look at how one can generalize the pole removal method to functions which are not rational. And then I'll briefly talk about how this method can be used for n by n matrices, which arise kind of in exactly the same situation where you have basically plates which are either arranged collinearly or arranged in some kind of number of different lines. So that's where the motivation for this work has come from, but of course it can be used in a number of other scenarios, and I will talk about the other related talks in this workshop. And what's nice about this method is that it leads to some iterations of something we can solve. So we start from a matrix and then we iterate some scalar, and we can make it so that we can do up to we can do hundreds of iterations very quickly. So if you choose the right basis and do it in the right way, then you can do loads of iterations. And in fact, the idea is that intuitively this is a natural way of solving it if you don't know very much theory behind it, and it does work. Okay, more on this, on the numerical implementation, will be in Matthew's talk on Thursday. So in this talk I will just describe the main ideas, and then Matthew will be talking more about numerics. He will be showing you what kind of the scattered field from some kind of 5 plates, 6 plates, and whatever you can extract and how you do the numerics. And also there will be some talks about how this method can be used in crack propagation problems by Pavlos later as well. Okay, so this is a very quick recap. This is a standard classical Wiener-Hopf equation, the nicest we can think of. And the standard idea is we want to factorize this function a, we multiply through, and then we do an additive decomposition of this term and arrive at this nice equation which has only plus functions on this side, only minus function on this side. So of course we then apply Liouville's theorem, and then everything works very nicely. Okay, what about pole removal method? So pole removal method relies on this function a being a rational function. So if this is a rational function, instead of factorizing this function, we can write it as a sum of a minus function and a plus function. And the reason we can do that is because we have a very simple expression for what the minus part of this function is, which is just a sum like that, and we can compute, and we know that those are just constants, right? So what do we do now? We subtract off those. So if we look back at this equation, if we did this minus this, we're going to get this plus side. So this is those two terms are plus. This is plus. This is minus. This is minus, and this is minus. Where this C minus is just an additive decomposition of this C. Okay, so very simple point to make. First of all, we can apply Liouville's theorem like we did before. But this is different from this equation. This is a very much a different equation. And second point, we're not done. After we apply Liouville's theorem, we haven't solved the problem. We have reduced this problem to finding n constants, which we can do by formulating a linear system of equations, and then we are done. Okay, so here are two different methods. And I guess I'm going to make some comments. And comment number one, you would say, well, if A was rational, we know how we can factorize a rational function, so there's nothing to do. We could have might as well done this method, and everything would have been well. Well, that's true. And Adukov here somewhere has written some code which does this, and there's a nice description in Spitkovsky overview how to do this rational factorization. Yes, one can do it, but this method applies to a more general class than just rational functions, as we will see later. Okay, and what's very important is that in approach number one, the fact if we go from scalar to matrix, the difficulty changes. We all know that we can do a multiplicative factorization of a scalar function, but we can't do that for a matrix function in general. On the other hand, this pole removal method doesn't care in some sense whether we have a scalar or a matrix system. We, in some sense, have treated this term in the same way we would have treated this term. So we just applied an additive splitting, and obviously this doesn't matter whether we have n by n matrix or not. Okay, another comment is that, of course, we could have not done this pole removal method, but instead just said we could have applied the generalized Liouville's theorem like in the previous talk, and just got it instead of here having some polynomial, we would have had just some rational functions, and then this would be equivalent to find those coefficients in some way. Okay, and Professor Speck told us a nice introduction about how to look at those from the operator point of view, and I'll be interested to discuss further how these two different methods compare in those more theoretical setting. Fredholm factorization, which Guido talked about in the previous week, I would want to say it only depends on additive Wiener-Hopf factorization. So in a way, it's more of an approach 2. You only do additive factorization. That's why it doesn't care about whether it's an n-dimension, whether it's a matrix or a scalar. And also, Olver's numerical method, which we heard about, again, only relies on the additive factorization, and we'll hear another talk later to do with the Wiener-Hopf stuff by Elena, I think on Thursday. And again, this only relies on the additive side. So in a way, this is kind of generalizing the pole removal method. And the method of Michuris and Rogozin, although it constructs a multiplicative factorization, the way it constructs this approximate multiplicative factorization, again, relies on steps which are all additive factorization. So there's another kind of, this is an idea which we've seen a few times now. Okay, so we've seen that rational functions are nice, they are friends, so why not just, instead of any function, have a rational approximation of that function? So we substitute some function by our friend function, and then we know how to deal with it. So let's look at an example, a very simple example. This is this function here. So this is y squared plus 1 over y squared plus 2, well, plus 4 square root. So very simple function, goes very quickly to 1. You can't imagine a kind of a simpler function to approximate. A nice way of approximating functions is using Caffadori-Fourier. I'm not going to go into details, but it uses Chebyshev polynomials and so on. So all we have to do is we have to choose an interval for this function, put put it into this Chapter, it will give us an approximation, and as we vary the degree of polynomials, we see that the error is decreasing, and we can decrease it more or less arbitrary. Note that this function goes to 1 very quickly, so the interval we have chosen, it pretty much is 1. So you would have thought that that works pretty well. But here is the problem. If you look on the complex plane, this is where the poles and zeros are. The function we initially had had a branch cut here, and that's what you can see there. But then we introduced all sorts of those poles coming, and in fact, the more, the better we get the approximation, the more poles appear. This is a massive problem, as we heard about poles encoding our behavior, kind of our physical solution. Introducing those poles is a really bad idea. We are introducing them also close to the real axes. Basically, this is no good. And the reason the reason that appeared is because we have truncated our real line to some arbitrary interval. Even though it looked very good, we were getting really small errors, it still doesn't approximate it very well. Okay, so solution to that is to apply a correct mapping. So the mapping maps the whole real line to an interval, and then we perform the rational approximation on that interval and then map it back. So this is just a combination of a Möbius map and a Joukowski map, which you can just explicitly write down. This is the map. You can think of it as you have this real line, you have the unit circle, you project it like that, and then you project it like that. So we have constructed a mapping from the real line to the interval. If you plot this new function after we did the transformation, it looks very nice. And then we can play the same game. We can do a rational approximation. Note that for smaller degrees, so that's just polynomial degree 5 by polynomial degree 5, we get a very small error. And then we can map this back to the real line. So this is this function mapped back to the real line. You see that the same error applies, and you can also easily verify that it's not only the initial function, but its factors, plus and minus factors, would also have even smaller error. And you can explicitly have some error bounds on those things as well, in nice spaces. Okay, and here is the magic. So the magic is that this time, after we've done this map, all the poles and zeros align perfectly on the branch cuts which we had here. So you see this is 10 to the minus 7. So you see they really do live exactly on there. And in some sense, why do I say this is magic? Because the problem we were initially solving has nothing to do with complex analysis. You get a real valued function on the real line. We're just doing an approximation. There's nothing complex about it. It doesn't know about the complex plane in any way. Okay. And in fact, you can see that it's not only the poles and zeros which align very well. We get a really good approximation. So this is some plot of the complex function initially, and this is the approximated function. So if we had to do any kind of contour deformation within here, we're all fine, because this function, if we picked any reasonable contour, would be exactly the same as the initial function we started with. Okay, so that sounds good. We have any Wiener-Hopf equation. We have some function in there. We just do a very nice rational approximation, and then we know how to solve it. Well, the problem is that the functions we care about are those gamma functions. So this is what Professor Speck mentioned in his talk as well. Those functions, unfortunately, do not behave like that at infinity. And this is the claim that Wiener and Hopf made in their original paper. And one of the lemmas, they started the lemma by saying, well, since this function tends to that, we can do this and that. And of course, this is only true for n being even, and it doesn't matter for a point of view of applications, because as David introduced it last week, they had even number of poles. So it doesn't change that behavior, but it does matter to us, because if we are going to do any rational approximation of this function, which is valid on the whole real line, we're going to fail, because we'll never catch this behavior. I should note that it is very much possible, and we can get good rational approximations of functions like that when you have two different constants here. So you have two different ratio like that, and that's something we've seen in one of the David's example later. Because this has finite branch cuts, we can very much do good rational approximations. Okay. So here I go, well, what is the motivation of what's to follow? It was a problem that my supervisor, Nigel Peake, has given me at the time, and I'm not going to talk too much about the motivation, because I think Justin will talk about it, I think on Thursday, about silent flight of owls and so on. But the idea is that you have a boundary condition on this semi-infinite line, and then you have some kind of impedance condition on this, and of course the usual edge conditions and radiation conditions and so on. And you can go through the usual Wiener-Hopf procedure to obtain this matrix system. Okay, and that's the matrix system I wanted to solve. And you will note that there are those gamma functions, which are bad for point of view of rational approximations, but there's another enemy we have. It's those exponential functions. So that's what Andrei mentioned in his previous talk. The fact that we have those exponential functions makes it more difficult. And obviously you can see that from the point of view of Liouville's theorem. When we apply Liouville's theorem, we wanted the growth to be at most polynomial. If you have exponentials in the wrong place, that's going to spoil it. Okay, so the first step in solving this problem in this method is to do a partial factorization. So we're not fully factorizing this matrix, we're only partly factorizing it. And what we are achieving is we're achieving that the exponential functions live in the right half plane. So this one with the minus is associated to this vector which has analyticity in the lower half plane, and this one with the plus is analyticity in the upper half plane. So we still haven't solved the problem, because we still have this term which has mixed analyticity. We still have this forcing term which has mixed analyticity. We don't worry about this term, because we know we can just do an additive factorization on that. That's what we usually do. This term is more of a problem. But what we do, what I propose we do, is we treat this term in exactly the same way we treat this term, and in an analogous way we do it for the pole removal. So we just say we write it as a plus and minus factors. That's what happens here. We simply wrote each, we have written this term as a plus and minus, and then we applied Liouville's theorem and we rearranged. We get this, and if we rearrange a bit further, we get those equations. Okay, and now if we look at this first equation, we of course see we haven't solved the problem. Like in the pole removal method, this is not, applying Liouville's theorem is not the end. We have this minus function here. We have this minus function here, the same minus function here. And then we have a different minus function here. But what's nice is that we now have this minus function with this exponential function. And this is the place where there's character development. This was our enemy. It caused us problems. But now it becomes our friend, because we treat it nicely. It became our friend. It's a decaying function. So the claim is that this term will be smaller than the other terms if L is large enough, if we go slightly above in the strip. Okay, and so somehow we need to solve this system. There's more than one way of doing it, but the simplest way of doing it is to omit this term altogether. So you see, if we omit this term, we can find what this is. After rearrangement, that's just the usual Wiener-Hopf equation. We find this term, we can plug it into here, and we find this one, and then we plug it into there, and we find this one, and so on. So if we know one of them, we know all of them. And the way that we're going to find approximately those functions is first assume something, that something is smaller than, we assume this term is smaller than the other terms, and then we're going to iterate. We're going to find this, we're going to plug it into here, and then we're going to plug the next term into there, and then we'll have an estimate for this term, which we'll put into here, and then again we'll solve, and we'll get a second iteration for this. Okay, so that's what this slide is explaining. It explains that if we omit this term, we can rearrange this equation into our standard Wiener-Hopf equation with a plus and the minus. And of course, we have this gamma function in there, but we can now not worry too much about it because we have a scalar equation, we can solve it. We can do our standard factorization here. Okay, so first thing I'm going to do is I'm going to show that it doesn't always work. So this is our first iteration, this is our second iteration. Well, actually, in fact, if you iterate more, it will work. But in this, it doesn't look like it's going to work. This method obviously works better when you have large L. So this is what you have. If you increase L, you get the acoustic field looking like this. And you see that the convergence is better. And you see that for higher frequencies, it's getting even better. So in some sense, for low frequencies, which we don't really care about because we have quite a simple solution, we're not getting what we want, but we are getting the right results for higher frequencies. And you can see that it really converges here. Okay, and this is just to say that we can extract some physically meaningful information about the size of this edge condition. Well, but I'm not going to talk about this here. So you can actually get results out of this method. Okay, what else? What we did for that particular problem obviously can be done for any matrix like this. We rewrote it as a system like that, and we can apply this iterative method, and we can prove that this iterative method works, converges, and we can have explicit error bounds for this. Of course, we're working in very nice spaces, L2, so that everything's very nice and we can get explicit results. We can compare this method to some known examples. So this is something which has been looked by Antipov and Abrahams. This is something we can do using pole removal. And you can see that doing it using this iterative method more or less recovers the solution after a few iterations. So for this simple 2x2 cases, we can do a few iterations, and for most cases, we get very good results. Okay, so, but the point is that it doesn't only apply for 2x2 matrices, we can extend this to n by n matrices, and this is an example that Andre talked about when you have two strips next to each other, and then you have to define 5 Fourier transforms. So I should draw a picture. So then we just define Fourier transform for each bit. Right. So this is not surprising. What was a little bit more surprising, at least for me, is that the resulting Wiener-Hopf equation had this form. So you see that this V1 was the function which was, yes, so this was the usual kind of the whatever plus function, and this was the minus function, or the other way around. And those are your analytic functions, they're free in the middle. And those analytic functions you can either take as plus functions or as minus functions, depending which exponential functions you pre-multiply them for. So basically, you have the plus function, the minus function, the plus function, and then those three functions you take either as plus function or as minus functions. And then the matrix just has your relationship, your physical relationship here, and then this is just the relationships between different plus and minus functions. Okay, and what we can do, we can rewrite this into the same form we had before. So again, we have the exponential functions in the right place now. Have the exponential functions in the right place, and we can iterate. I'm not going to say more about it now because Matthew is going to talk more about how one does that on Thursday. Okay, so quickly recap what has happened. We have constructed an approximate method with bounds in L2. We know we exploited the solution to the simple subproblems. What I haven't really talked about is that those, when I was neglecting certain terms, you can think of it as generalized, kind of as the same as Schwarzschild series. The difference is that you're doing those iterations in the Fourier space rather than in the physical space, and you can do, I mean, most papers you see this technique applied, they do 1 or 2 iterations. Here we can do hundreds of iterations with no problems for loads of edges. It has a lot of nice limits. It uses the same idea of additive factorization, which I think is very important when you go from one-dimensional to n-dimensional matrices. And of course, as I said, Matthew will talk about how one makes it work numerically, and also Pavlos will talk about how one can use the same ideas in crack propagation problems. Okay, moral number 1, that additive factorization is good. Moral number 2, multiplicative and additive factorization working together is even better. And thirdly, if you want to produce accurate numerical results, you need to be careful about which mappings you use and which base functions. So that's critical to get good numerical results. And this is maybe some questions, whether someone knows how to compute partial indices of the type of matrices I have shown, what are the partial matrices mean physically, and in general, there's a lot of approximate methods in the applied community. Can we come up with good ways of creating error bounds for those methods? So that's more general than just for this technique, but maybe something we can discuss later.
Thank you. Open to questions.
Right. So this partial factorization you mentioned somehow reduces the problem to factor a matrix which contains square roots and oscillating terms to something else. What is the spirit of this? What is the result? What can you better in this partial factorization?
This one here. So what we're doing here is we're simply dealing with one problem at a time. We have 2 problems here. We have problem number 1, that those functions are not analytic where we want them to be. And problem number 2 is we have those exponential functions which don't behave correctly. So you can show that for n-dimensional matrices as well of this, that you can always split it into 2 parts, where one exponentials will kind of exponential growth and exponential decay will kind of be in matrices of diagonalish form like this.
So there's Jones's method in Noble's book, which essentially solves these same problems, but they take the bits with the exponential behavior in them and puts them in an integral equation form. So for large L, his method works superbly well, as does yours. The iteration gets better. His is not very good for small l. How does yours compare?
So this actually does very well for small l. It's just number of iterations. So if you're interested in getting good results in 3 iterations, then you should take fairly large. But if you have coded up correctly and you can do loads of iteration, then it converges in cases where you would have thought it wouldn't converge. That's what he found, at least. Yeah.
When you numerically approximated your function in the right way, choosing your mapping, then you had these poles on the cut.
Yeah.
Do you have a 0 between each pole?
Yeah, that's right. So you have alternating zeros and poles, and what you have is you have infinity and 0 close together, and that somehow is the same behavior you expect from branch cut, right? When you approach essential singularity, you take all the values, right?
And so what's how does it relate to the Padé approximant? Because you seem to have the same type of result.
So
Are
the
they
Padé
connected?
approximant doesn't give you that instability of the sort of ring of poles and zeros if I do it with exact arithmetic. But as soon as I do it with approximate arithmetic, I get numerical error, which is tantamount to the same problems that you get. But in a way, that's better though.
So this is
Using
more
Cheb-
stable in some sense.
Mine is more stable,
Okay.
Padé approximants, than Cheb-Fun, because it's intrinsically a sort of numerical approach. But this is a discussion for later.
Is it the same? Are they at the same location, like the
No.
approximation?
No, I mean Cheb-Fun chooses the points. So I mean Padé, you take 0 and infinity,
Well,
which
you
is
can use multi-point Padé approximants to get round problems with infinity. Yeah,
yeah.
they're not the same, but they're related. Gennady.
I had only small comments. So I believe that method what is suggested with Sergey would work much better for small l, and it's not. I believe so. This we know that method working perfectly for small l, and then become not so nice when you increase the l. So in that sense, this is 2 options. If one would like to have this absolutely effect, then to take both from different levels. But when we did ours, so we also considered was taking into account what is the partial indices there, and I think all the methods would become nastier when we go to the partial indices not equal to 0. So
Yes, but you have to show me a physical problem with partial indices not being equal to 0, and then we'll talk. Okay, good.
Any final questions? If not, can we thank all of the speakers in this session? Very interesting session.